interested in something like a knot complement, you can start by drawing just a projection of the knot or link using a mouse. I guess if I have time, I might give you a brief demo at the end today. And then you can start finding hyperbolic structures on this link complement and manifolds obtained by Dane surgery. More generally, you could just start with some sort of description of a manifold as a triangulation, an ideal triangulation. I should mention, okay, the latest version of this, I mean, this has been developed over many years, and there's a number of different versions. The latest version, which has a kind of new Python interface, it's called Snappy, or SnapPy, written by Mark Cullen and Nathan Dunfield. So this is kind of the latest version if you want to get a copy. Okay, so how does Snappy work? So we start off with some cusped manifold. So it might be something, say for instance, a link complement, or you might have a triangulation description. First step is to find a sort of ideal triangulation. So this is just a topological triangulation for your manifold. Now, a very important step is actually next to try and simplify the triangulation. Okay, so the first triangulation you come up with, it might be quite complicated. And I think one of the sort of secrets of Snappy success, it's very good at simplifying triangulations. So there's a few sort of basic moves that you can do here. What's it? So two sort of basic moves are these, I'll call them, so 2 to 3, 3 to 2 moves. So if you imagine you have two tetrahedra meeting along a triangle in the middle, then you can change the triangulation by adding an extra edge. So we put an edge going through the centre here. Now, if you look at this, you now have another triangulation with 3 tetrahedra meeting along this edge. So by using this kind of procedure, you can go from 2 tetrahedra to 3 tetrahedra, or vice versa. And in fact, it's known that you can get from any triangulation to any other triangulation by a sequence of these kinds of moves. So that's a result of Matveyev and Pergolini. Okay. So the idea is to simplify the triangulation as much as you can, try and cut down the number of tetrahedra and so on. Next step is to solve the gluing equation. So that's these sort of the edge conditions and these completeness conditions that we were talking about. So this is some sort of system of polynomial equations. And what Snappy does is just solve these numerically by using Newton's method. Okay, and as a kind of starting point, the first guess is to assume that all the tetrahedra are regular. Okay. And in practice, okay, this works extremely well. Once you've simplified the triangulation, usually Snappy will very quickly find you a solution with positively oriented tetrahedra, giving a hyperbolic structure. And you can also do this with hyperbolic Dane surgery by adding these extra sort of holonomy equations that I talked about before. Okay, so this is all sort of numerical calculations based on Newton's method. Now, once you've got the hyperbolic structure, so if this all succeeds, you have numerical descriptions of the shapes, the complex shape parameters for all the tetrahedra, and this actually tells you everything about the geometry. So in principle, you can start computing any kind of geometric properties that you like. For instance, you can find an exact description of the holonomy representation for the hyperbolic structure. So that will give you an explicit discrete subgroup of PSL2C. So that's another thing you can read off. And then you can start calculating all sorts of geometric invariants. So maybe we'll come back, I guess, and talk a bit more about these later. But For instance, there's things like the volume. There's a hyperbolic volume of the manifold, lengths of closed geodesics, and many other things which maybe we'll talk about later. So actually, again, by Mostow-Prasad rigidity, because the hyperbolic structure is unique, these are all sort of topological invariants of your manifold. So this gives you lots of important topological information and ways to compare or show that manifolds are not homeomorphic. So for instance, if you get manifolds with different volumes, you know they can't be homeomorphic. So you can use this to help start classifying these manifolds. The other thing, turns out there's actually a way to test trisometry. So you can decide whether or not two of these, say, cusp manifolds are isometric by using the geometry. And this involves coming up with some sort of canonical triangulation, or more generally a canonical cell decomposition, which is defined completely in terms of the hyperbolic geometry. Okay, so this is something developed by Epstein and Penner. And this gives you a way of deciding if two cusped hyperbolic manifolds are homeomorphic or not. The idea is you can compute this canonical cell decomposition, and that gives you some sort of combinatorial description of the manifold with tetrahedra glued together by some sort of combinatorial gluing maps. If you've got two manifolds, these things have to be the same. So if the two manifolds are homeomorphic, if and only if these canonical decompositions are combinatorially the same. So this actually solves the sort of homeomorphism question for these cusp hyperbolic manifolds. Okay. Now I guess at this stage, okay, I want to mention, so one important open problem. Basically, Snappy works extremely well in practice. It's very fast, it's very efficient, seems to do everything you'd hope it to do. But there's no kind of good explanation of why it works so well. So I think one basic open problem is to prove that there's efficient algorithms for computing hyperbolic structures on three manifolds and orbifolds. I guess it's known that algorithms exist for doing this. I guess this goes back to ideas of Casson written up by Jason Manning. This basically, I guess these algorithms basically involve finding all suitable representations of the fundamental group into PSL2C. You look for kind of representations that are kind of rigid up to conjugacy. There should be a finite number of these. Then you can, if you can find them all, then you can try and show that show that these are discrete. You can check the volume, and the one with the biggest volume would have to be the hyperbolic structure. So there's this is basically involves finding all representations of the fundamental group which are kind of rigid. And it's not really feasible to do this. Okay. On the other hand, Snappy works extremely well, and a big problem, I think, is to show why it works and to prove that there really are efficient algorithms that are guaranteed to always work. I think the main problem here is to understand how you can come up with a good triangulation in a canonical way. So you're given your manifold with some kind of arbitrary triangulation. I guess it's not, so Snappy does very well at simplifying the triangulations down to something which is actually geometric, but there's no kind of proof that there's a good general algorithm for doing that. So I think this is an important question. Okay. The final thing I wanted to talk about today is another program called SNAP. This is basically an exact version of Snappy. So Snappy gives you numerical solutions. SNAP allows you to find exact descriptions of hyperbolic structures. For instance, you might be, these complex parameters turn out to be algebraic numbers. And you should be able to give exact descriptions of these algebraic numbers by giving them minimal polynomials, for instance. And this is the kind of thing that SNAP can do. So this was written by Oliver Goodman, I guess working with Walter and myself. Okay. So the idea is to find exact descriptions using algebraic numbers to describe the parameters exactly. And then once you've got that, you can also compute lots of interesting arithmetic invariants. So I think Walter will talk a lot more about these probably at some stage. Okay. So this program, SNAP, it's based on SNAPPy together with a computer program for number theory called Paris. So it combines these two things together. And I just, okay, so I might ask, so why do we expect things to be algebraic? Well, again, it basically comes from Musto rigidity. So for instance, that will actually imply that the complex edge parameters I was using before are actually algebraic numbers. So they satisfy some polynomial equations with integer coefficients. And so why is this? Well, the basic idea is they lie in an algebraic variety. So we look at the solutions to Thurston's gluing equations. That's some kind of system of polynomial equations, essentially, with integer coefficients. Musto rigidity says you get a zero-dimensional solution space. And then from a bit of ideas of algebraic geometry, you can see that each of the coordinates has to be an algebraic number. You can use things like resultants, for instance, to get a polynomial equation satisfied by each of these complex parameters. Or there's other things like Grosvenor bases you could use to get polynomial equation for each of these. Now, I guess in fact SNAP doesn't actually use things like resultants or Grosvenor bases to try and find these exact solutions. It actually does something, well, a bit more interesting, or surprising maybe. So here's how it works roughly. First step is to compute hyperbolic structures numerically, but to high precision. So SNAPPy works with something like maybe 16 digits of accuracy. This is kind of standard floating point arithmetic. SNAPPy, so SNAP can actually work to arbitrary precision. And typically we might work with, say, 100 to 200 digits accuracy for some reasonable size manifold, 5 or 10 tetrahedra. And then the idea is once you know a sort of a high precision approximation to the, say, the simplex parameters, we try to guess the exact solution, okay, and describe it precisely as algebraic numbers. Okay, so this sounds very surprising, unlikely, but it actually works very well. So here's the idea. So if you've got some number which you know is algebraic and you've got an accurate numerical approximation to this algebraic number, what we're going to do is try and guess the minimal polynomial for z. Okay. So if you succeed in doing this, say for all the simplex parameters, then you get an algebraic number field which contains all the simplex parameters. And then you could check that your guess is actually correct by looking at these polynomial equations and substituting in your proposed solutions and doing exact calculations in this number field. Okay, so that's the basic idea. So you first guess the solution and then you can check it by doing calculations in this number field. Okay. Okay, so the question is, so how do you guess minimal polynomials? Well, this uses a famous LLL algorithm, which basically gives you a good way of finding short vectors in an integer lattice, which is equipped with some kind of inner product. And here's the basic idea. So suppose you've got, so Z is some sort of numerical approximation to some algebraic number tau. What we're going to do is look for an integer polynomial, let's say bounded with degree less than or equal to m. So we might assume, okay, we're looking for a polynomial of degree less than or equal to 20. The idea, we'd like to try and find a simple polynomial, meaning that coefficients are not too big, which is very small when you substitute in this numerical value z. Of course, so if you get the right polynomial, you should get 0 to sort of whatever numerical accuracy you're working with. Okay, so how do we do this? Well, what we do is try and pick the coefficients of our polynomial. So we're going to have coefficients a0, a1 up to am. So these are going to be some integers. And we're going to look at, say, the sum of the sizes of these coefficients, the sum of the squares of the coefficients, plus something which is basically some large constant times the size of this polynomial with z substituted. Okay, so I guess at the end this is supposed to be an times z to the m. Something happened there. Okay, so you've got the coefficient squared. You've got the size of the polynomial when you substitute in z. So we take the absolute value of z squared and we multiply by some large number, which will be roughly something like 10 to the 1.5 times d, if you know z to, say, d decimal places of accuracy. Right, so typically we might, have n equals 100. So then, sorry, d would be about 100 maybe. So n would be really large, something like 10 to the power 150.
What is that small n?
That's a typo at the end there. So let's see, that's supposed to be. We just take the value of the polynomial. So we get a0 plus a1z plus am times z to the m. So we take the size of that all squared multiplied by this constant. Okay, so that's what that was supposed to be. So what's the idea? So the idea is if this thing is small, so first of all, it means that this part is small. And that means that your z satisfies this polynomial to some high accuracy. This part here is kind of to try and make the size of the coefficients small as well. So, okay, so this is what we do. So that's some sort of quadratic form or Hermitian form on this integer lattice. And if LLL succeeds in finding a short vector with this kind of norm, then what it means is probably that, if you're lucky, that tau satisfies this polynomial exactly. And so then you've got some sort of integer polynomial satisfied by tau. This may not be the minimal polynomial necessarily, but you can always factor it and pick out which factor contains this tau as a root. So this is how you can try and guess the minimal polynomial. Okay. Now you can do the same kind of thing. If you've got one parameter, if you look at the next parameter, you can try and write it as a polynomial in the previous parameter. Again, you can use the LLL algorithm to do this. And you can continue in this way to try and get an algebraic number field containing all the simplex parameters. Okay, so then at that stage we've got everything in a single algebraic number field. We can just look at the original polynomial equations and check if we have an exact solution. So if this all works, what we've got is actually a rigorous proof that our manifold's hyperbolic, but we also get an exact description of its hyperbolic structure. And we've got a minimal polynomial for each of the parameters, and we also know, which root it is from the numerical approximations. And then you can do lots of things. You can start computing many other interesting invariants, things like the invariant trace field, invariant quaternion algebra. So I guess Walter will probably talk more about these later. And you can also decide, for instance, if the manifold's arithmetic or not. So this gives you a whole another class of powerful invariants from the manifolds. Okay, so I'll stop there, and thank you very much. Let's put up the list of references again if you want to look at those. Okay, thanks.
Any questions?
Okay.
Okay, that's thanks.
Okay, thank you.
Beautiful lecture.
Thank you. Thanks.